We like to think of stars as eternal. In human terms, they are. But we know that's untrue cosmically. They grow hotter and expand. In 1 billion years, the ocean will boil. And in 5 billion, the atmosphere will be a memory. This is the passive path, the default setting of the universe. To stay here is to accept an expiration date. But what if we paid to change it? What if we become the governors? And will physics allow such a thing? To stay alive, we need to exploit the sun so it doesn't heat up the solar system. Luckily, we know that big stars die first, and small ones die last. The main sequence lifetime shrinks sharply with its mass. Roughly, T is proportional to m to the exponent of minus 2.5. Because of this steep drop-off, even a percentage of decrease in mass increases lifetime by roughly a couple hundred million years. Seeing it this way turns the sun into an engineering problem. So in theory, engineers would need to pump out a percentage of the sun. This works because less mass means less internal pressure, decreasing the rate of fusion, extending the sun's lifespan. For the first time, the sun ceases to be a cosmic countdown, and now in the hands of humanity. In order to perform this miracle, we need to be pumping out a certain amount of mass. How much exactly? Around 0.05 Ceres masses each year. A dwarf planet's worth of material slowly siphoned away. That breaks down to roughly more than 8 times the total mass of the Earth's atmosphere, gone in just a year. This scaling is why shaving a fraction of a percent of mass over geologic timescales buys whole billions of years of deliberation. If pumping out that much mass can buy us billions of years, what is stopping us from trying? Stars in general are stubborn. There are 3 constraints that we must consider in order to drive it. The first is shear lag. If we pump out massive amounts of masses such as 0.05 Ceres per year, the sun wouldn't react for tens of millions of years. Why? If you took out a chunk of the sun, the chunk contains energy and heat, meaning heat is removed from the system of the sun. But the question is, how long it takes for the sun to diffuse into a new thermal balance again. That is, the Kelvin-Helmholtz timescale, around 30 million years for our sun. And roughly every 100 million years, our star's luminosity grows by 1%. By that time, Earth's climate would have already shifted in response to the small changes in sunlight. The lag forces humanity to start interventions long before the first visible warning sign. Then secondly, the butterfly effect. A small perturbation can cascade into a catastrophe. A miscalculation can scoop up helium from the core and accelerate the very expansion we're trying to slow down. Dragging helium ash up from the core and dumping fresh hydrogen into it all at once would cause a stellar Chernobyl. And stellar evolution is an infamously challenging field, leaving us to almost gamble on all of life. Lastly, there is coupling. The sun has layers, acting on the photosphere, the surface, does little to affect how fast helium burns at the core. Surface changes barely change what happens inside. If we fail to couple the surface to the core, we might successfully shrink the sun, but its unchanged core continues to cook the Earth, leaving us with a smaller, even more concentrated nightmare. These limits don't condemn us to fate, but it does demand careful engineering, knowing what works and what doesn't. Humanity can make its first step into the art of starlifting. To defy the ledger, we have 2.5 paths of rebellion. The most controllable in theory is to remove stellar material as a constant outflow. Core pressure and temperatures can remain lower than they would have been otherwise. That could happen through magnetically guided siphons or intense plasma ablation by concentrated energy. Pulling out 0.05 Ceres for 1 billion years siphons out 2.4% of the sun's total mass. Just even 2% rewards up to 500 million years in return. But it's also the most unforgiving if mismanaged. Pulled too deeply, mixing wrong layers. The sun doesn't dim, it brightens. Permanently. Humanity is then left with less time. There exists a far safer route to save Earth, although speculative, and that is to spin the star. Whether passively or actively, you've heard of the Skarov thrusters, passive reflective mirrors that push back light and move the sun in a million years. But instead of moving, we torque. In this way, gravity is counteracted by the centrifugal force near equatorial regions, causing less pressure to the core, thus lowering fusion rates. For maximum effectiveness, the star must spin at near critical rotation rates, where gravity barely beats the centrifugal force. How do we do this? Simply place mirrors that redirect light to the equator of the sun, inducing minuscule forces. However, it takes a billion years for any change, therefore barely useful. The active way solves the timescale problem, but high risk. Because the sun is very magnetically active, we use that as our leverage. Anchor massive magnetic nozzles near the equator of the sun. Extract ionized plasma from the photosphere or the coronas. Then the plasma is trapped into the strong magnetic nozzle. Concentrated energy accelerates the plasma forward in narrow streams. These streams fire out at extreme speeds and collide with the surface of the sun, nudging the whole star to turn faster minutely. But this time, it takes a few million years. Using the same theory, lowering pressure for the core and thus also fusion rates, also causing hydrogen to move into the core, extending lifetime. This not only requires enormous energies and continuous flows, but can cause a catastrophe if too fast. Worst case is the sun ripping itself apart. The physics doesn't forbid any of these. What forbids is carelessness, and it's up to humanity to take it seriously. The hardest part isn't even the machinery, it's making sure that the machinery outlives belief. Every generation must choose to keep running systems that they didn't design, for a threat they'll never see, for an outcome they'll never get to see. Every 50 years, a new operator replaces the old. In just 100 years of humanity, language evolves, knowledge shifts, and priorities change. The words and concepts used to explain this project will most likely drift into obscurity. Is it even ethical to force responsibility on the next generation to keep running a mega project from the past? A past so long ago that it surpasses the existence of Homo sapiens tenfold. A project that lasts millions of years requires a biological miracle to keep supervising, because supervising reads as a measurement rather than a triumph. The control room stays dark, no flashes, just graphs of solar pulses, data of the sun's rotation, or solar flares every now and then. Tiny moves matter the most. Add a fraction of more pull on the mass, or increase rotation, century after century. Systems repeat themselves everywhere. People meet now and then, checking progress over time. A supervisor's day is quiet and exacting. All this effort serves one purpose: to keep the sun from growing brighter, larger, and hotter. To succeed is to make the sun look the same. To an alien observing our sun from the night sky, it looks unremarkable against all the other stars. Performing this miracle is inherently silent, but that is terrifying. What if we are the aliens? What if we are the ones who observe the night sky, clueless that we've already seen an engineered star, but just didn't know it? Hauntingly, a perfectly managed star looks ordinary. Maybe somewhere, some civilization is already doing the bookkeeping. Their star appears unremarkable to us. The proof of supervising is silence. The things that don't happen across millions of years.